This is the second lecture concerning a classical description of the electron, and this classical model of electron is going to be applied for the classical description of the tunnel effect. The tunnel effect is called as this in quantum mechanics for the crushing of a beam of electrons to a potential barrier. And it is said that this effect is a pure quantum mechanical effect, that it has no classical interpretation. Nevertheless, this is not completely right, because the usual classical interpretation of the crossing of potential barriers is usually performed with the spinless model of electron, with a point particle electron. But the electron is not a point particle. The electron is a spinning particle, and the spin plays a fundamental role, in particular in the crossing of this potential barrier. We can show that, in fact, the spin orientation is crucial for the crossing of a potential barrier. What is a potential barrier? A potential barrier could be a device like this: three parallel conducting plates, electrically charged, the outer plate positive charge, the inner one negative charge. There is a difference of potential V0 between the outer plate and the inner one, so these lines represent the existence of a uniform electric field inside. The electron has negative charge, so if it is in this region, it is under a force to the left, and if it is in this part, it is under a force to the right. So to analyze this static field analysis, the potential energy of the electron in this device is 0 outside the plates. It rises up to a maximum top of EV0, decreases, and vanishes outside the plates. So let us make the theoretical analysis of the electron with this triangular potential barrier. We accelerate electrons with an acceleration potential VA below V0, so that the kinetic energy of the electron on the left-hand side is constant while the electron is outside the electric field. Because fields are conservative, the addition of potential energy plus kinetic energy is constant, so when the electron penetrates in this region, potential energy rises so that the kinetic energy decreases up to 0. This means that in this point the electron stops, it is under a force to the left, and therefore it will be rejected. So we can see something like this. Electron stops and is rejected. Once again, stops and is rejected. So it is impossible that an electron with a kinetic energy below the top of this potential can cross this barrier. This electron can never go to the right-hand side. Well, let us perform the experiment. The experiment will be this. We have the three plates. We locate on the right-hand side an electron detector and accelerate electrons with the same acceleration potential VA below V0 and send to this potential barrier. What we see is something of this thing. The electron is repelled. In general, electrons are repelled. They never cross, in general, this barrier. But sometimes some electrons cross the barrier. How is it possible if the theoretical analysis forbids this? Nevertheless, the electron has crossed the barrier. So there is some inconsistency in the theoretical analysis. Well, it is true. In quantum mechanics, we say that if the electron is on the left-hand side and it is under this device electric fields, the wave function for the whole process has a part of the wave function, a non-vanishing part, which is resting on the right-hand side. So quantum mechanics says that there is a probability of crossing. Not all electrons cross the barrier, but quantum mechanics predicts how many electrons can cross. The average number of electrons that can cross this barrier. But the inconsistency is that this experiment is performed with real electrons, which are spinning electrons. But the theoretical analysis has been done with the point particle electron, which is a wrong model for the spinning electron. So, in quantum mechanics, they say, oh, electrons have crossed this mountain. They do not have sufficient energy to climb the mountain and go to the other side. So they have drilled a tunnel through the mountain and crossed the mountain to the other side. That's why this effect is called tunnel effect. But the point particle falls with this. But we shall see that if we use the proper model of a spinning electron, it can cross the barrier, but it depends critically on the spin orientation. Okay, the model we have obtained in our formalism, I showed in the first lecture, is this. The spinning electron at rest means that the center of mass is at rest, but the center of charge is a different point, and it is moving around the center, continuously around the center of mass at the speed c. So in the center of mass observer, this object has a kind of rotation, and therefore has a spin. And the spin has two parts. One related to this orbital motion, z, and another related to the rotation of a co-moving Cartesian frame attached to this point, which rotates with angular velocity omega. So this w part, in addition to this zeta part, gives you the total spin. So we are going to use this spinning electron model, which satisfies Dirac's equation when quantized, to analyze the crossing of the barrier. We can send the electron with the spin pointing forward or backward, so in a longitudinal polarization. It means that the center of charge is moving transversally, or alternatively, the second possibility is the second one, where the center of charge is turning around in this direction. We can produce these spin orientations with an external magnetic field. Magnetic fields produce orientation of magnetic moments. The needle of a compass has magnetic moment, and it is oriented along the external field. Electrons have magnetic moments, like compass needles. So, if I introduce a magnetic field, I can orient the magnetic moment of the electron, and therefore the spin of that electron. Of course, we can analyze different spin orientations for the crossing of this barrier. This effect is called spin polarized tunnel effect. We can take the dynamical equations of this model in this electrostatic field. We can analyze the integration of the differential equations. I have not been able to obtain analytical solution in this case, but I will produce a numerical integration. To produce the numerical integration, I have a computer program in which I have introduced the dynamical equations of that model. This is the potential barrier. I will describe here the evolution of the kinetic energy of the electron while it is moving in this area. It is a function of the center of mass position. In the lower part, I will describe the evolution, the projection on the x plane of the center of charge motion. The first integration is performed with the spin forming 90 degrees with the z-axis, so it is pointing the spin along the x-axis, and see what happens. I have stopped the integration just now. Oh, okay. So when the particle penetrates into this barrier, the kinetic energy decreases up to 0. Here the electron stops. This is the projection of the center of charge motion. It has stopped here. I erase this previous integration and let the program to go on with the integration. Oh, finally, the electron is rejected. Spin polarized electrons pointing forward or backward never cross the potential barrier, like the same thing that happened to the point particle model. It is the same. Now let us turn the spin pointing upwards 0 degrees and with the same kinetic energy and see what happens. Oh, the electron has crossed the barrier. What is happening here? When the center of charge enters into the electric field, the kinetic energy decreases. But when the center of charge is outside that region, the kinetic energy remains constant. Decreases, remains constant, decreases, remains constant. When it is completely inside this region and the center of charge reaches the right-hand side area, the kinetic energy increases because the force is to the right. So here it decreases, increases, and so on, and the final result is that the electron has crossed that barrier. Or one can say, oh yeah, this is because now the spin orientation is strictly pointing upwards. Well, I can do the same thing pointing, for instance, 60 degrees. I take 60 degrees orientation, I erase this previous orientation, and now I take 60 degrees orientation of the spin. Oh, the same thing happens. It also crosses the potential barrier if the orientation is not explicitly longitudinal direction. Oh, one can say, oh, this potential barrier is too narrow. And in fact, the width of this potential barrier is 4 times the radius of this internal motion. Of course, I can increase, for instance, the right-hand side barrier to a value of 8 times this region, and see, in this case, what happens. Oh, with that orientation, it does not cross with that energy. I point the spin upwards, and it crossed the barrier. Oh, one can say, oh, the left-hand side barrier is too narrow. Okay, let us increase the left-hand side barrier and go ahead. Okay, it also crosses. So the conclusion, longitudinally polarized electrons can never cross the barrier, like the point particle model. But if we have arbitrary orientations, there always exists a minimum kinetic energy, such that with that kinetic energy and above, although below the top of the potentials, all electrons cross the barrier. So there is a classical explanation of the tunnel effect, but using a model of a spinning electron, not with the point particle model. Okay, we shall apply these ideas to analyze what are called magnetoresistant materials. These materials are typical electronic resistors. But these resistors are made of small droplets of small conducting grains held together under high pressure. It is called sinterization. These conducting grains, they are separated from each other from some distance, like this. These devices are very bad conductors, electric conductors, because it is not a continuous conductor. Electrons has to jump from grain to grain if they try to conduct electricity. So when electrons try to jump from the first grain and leaves the first grain, the grain remains positively charged because it has loose an electron and attracts the electron. And if the electron is closer to the second grain, induces an electric field here, so it is positively charged and it is attracted to it. So the electron which is in between these two conducting grains is under a force to the left or to the right depending on this position, so it is like a kind of potential barrier inside that region. And we know how to manage potential barriers by using magnetic fields. If I introduce a magnetic field in this direction, spin electrons polarize in that direction, so there will be no jump of electrons between grains. This kind of magnetic field prevents the crossing of electrons, and this device is a device of a colossal or giant resistance. But if we introduce a transversal magnetic field, there will be many electrons which can cross the barrier, and basically the electrical resistance of this device is quite low. It's almost zero. Well, this device is used as the reading head of a magnetic hard disk. The magnetic domains recorded at the magnetic disk have two orientations: longitudinal orientations or transversal orientations. The longitudinal orientation, when the head goes through that part, prevents the crossing. The transversal orientations produces the crossing. So the zeros and ones recorded in the magnetic disk are transformed into the current occurring through this electronic device to recover the data recorded at a magnetic hard disk. Okay, the formalism which describes this model of electron has been developed in this book, or you can alternatively discharge these two documents of a previous lecture course. You can contact me. All these numerical integrations of the dynamical equations have been performed with the Dynamics Solver program, and there are another two lectures concerning this classical structure of the electron to analyze these two phenomena, and the final one devoted to the introduction of the dynamical equation of the spinning electron. Thank you very much for your attention.